So in this chapter 5, like I mentioned, we are going to start evaluating atmospheric stability. We started with observations like pilots do. We're going to move in this video into environmental lapse rates that we see on soundings. From there, we're going to take a more focused view and look at calculating the cloud base or the level, the altitude where the cloud starts, and the cloud temp as it grows and rises. And we're going to do that by comparing lapse rates. Then we're going to take a much narrower view and figure out what cloud type we're going to have based on lapse rates again. And then we're going to take a very narrow view and look into the process for creating rain droplets. So we're going from the atmosphere all the way down to the rain droplet in this chapter. When it comes to lapse rates, let's start with the environmental lapse rate that you learned back in chapter 1. You can go back to chapter 1 to look at this, but you learned that the average environmental or atmospheric lapse rate in the troposphere only is approximately 6.5 degrees Celsius drop in temperature for every 1,000 meter gain in altitude. So in other words, what you're looking at in the troposphere, and this is part of your chapter 1 graphic, is that if you start at, your average 57 degrees Fahrenheit on Earth temperature at sea level, then you will lose approximately 6.5 degrees Celsius for every 1,000 meters. So what we have here is I have the Fahrenheit chart here for you to refer to and the Celsius chart, but we are looking at the Celsius, the metric lapse rate. That is the average lapse rate all the way around the world, equator to poles and everywhere in between. We calculate this lapse rate, just as a review, by dividing the temperature change in the environment from here to here by the change in altitude, so that I am saying this is 6.5 degrees Celsius per 1,000 meter altitude. That's your average environmental lapse rate. Averages as a very wide range. Let's look into how this average expresses itself in observations that we know. Again, I'm going to go back to pilots. You will note here that the ground warms the air, and the ground is warming the air by radiating off its infrared energy so that it will warm the air and stop the air from losing so much warmth. And so you'll have generally a gradual decline in temperature as altitude increases. This could be right around 1,000 meters here because we've lost about 6.5 degrees Celsius between 15 and a little under 9 degrees Celsius. So this pilot is flying at approximately 1,000 meters. That is what we refer to as the observation for the lapse rate. The data that we collect is from radiosondes, and the data is expressed in charts and graphs. And we look at this as a lapse rate that looks at differences in temperature. The Celsius is down here in green. Kelvin is actually in black. And we look at it in terms of altitude here in meters. We also look at it in terms of declining atmospheric pressure all the way up to the stratosphere. So this is how a lapse rate looks on a graph or a chart. This is called a Stuve diagram. We're going to be using Stuve diagrams in our course. The other diagrams, SKU-T, are a little bit more complicated. We're going to start here where it's simple. Now, you would notice here that you've got some strange things going on here at near ground level. Let's talk about what happens at ground level, and then we'll talk about what you're noting here as well, which is very common overnight. So let's talk about what happens from the ground up. We have a we have a pattern of forced lift from the ground up. Remember, the ground conducts to the first few inches of air, and then you got to get the warmth from the first few inches of air throughout the entire atmosphere. We do that by a combination of techniques in forced lift. Let's look at the first one that you know really well. The first one that you know really well is convection. That conduction happens right at the surface, and then warm air rises, right? And you know that is convection. So warm air rises and expands and cools and may condense. One of our first forms of forced lifting is convection. You go from conduction to moving in an updraft and lifting via convection. And another compounded convection is force lifting by convergence of convective parcels. For instance, pretend this is Florida or Orlando, Florida. And you know when you go to Disney World, the first thing you do is that at 4 o'clock in the afternoon, you head for a cafe because it's going to rain. And it's going to rain in part because of this forced lifting issue. You have convective parcels coming off of the warm land on the western side of Orlando and moving up in an updraft. You have convective parcels coming off the eastern side of Florida, and they are moving in because they are being pushed by sea breezes from both the Gulf of Mexico on the west side and from the Atlantic on the east side. When they are pushed together, these two convective forces, they butt heads. When they butt heads, the only way to go is up. So this is called a convergent lift of meeting minds, and they go up on a very forceful lift here that will often produce rain. So convective lifts can condense and produce precipitation, but convergent lifts are a little bit more powerful because they have two of these systems moving together, and they often will produce rain at 4 o'clock in the afternoon in Orlando. Here is an infrared satellite photo for you of cloud buildup and convective and convergent cloud buildup from the Gulf of Mexico and from the Atlantic right over Orlando. So this forced lifting is a very important part of the climate in many parts of the country. Another type of forced lifting in another part of the country is topographical forced lifting. When air is blown on a prevailing wind at a mountain range, there's nowhere to go but up. So that air moves up on what's called a forced topographical lift. I call it a topographical lift. It is also called an orographic lift, but I think topographical lift is easier to remember. So here's another type of lift that is critical to the climate of the Rockies, and it also impacts the climate of the Appalachian Mountains as well, this forced topographical lift. In addition, you should know that, we went over that, topographical and orographic lift and no way to go but up. We'll be studying this entire phenomena in our assignment this week on rain shadows. And when we come back to look at the sounding, we can see the forced lift on the sounding. In other words, you started at ground level here, and we started warming the air from the ground level by circulating the air with these lifts: topographical lift, convergent lift, convective lift. There's another type of lift, frontal lift. We'll learn more about that in Chapter 8. So we see here that we're starting to circulate the air here, and that is making the atmosphere warm a bit above the ground. Now you may say, it doesn't look like the atmosphere is warming a bit above the ground because I see the temperature declining, or I see the temperature moving into lower numbers as altitude increases. And I will point out to you that if we didn't have the circulation that it was involved in lifts, then you would see a slope here that lost temperature very rapidly over the first 100 meters of altitude, because the ground would stay warm and there would be no circulation up into the atmosphere, and so you would lose temperature very rapidly in the atmosphere. By circulating the air, we're actually keeping the first 100 meters or so warmer than it would be. That's what the data is showing to you here. Now, you notice a very strange issue right here. We're going to talk about that on the next video.